Okay, first type of intermolecular force that we have is known as a dipole-dipole force. Okay, so the name of this force is a dipole-dipole force. What the force is, or how it is formed, is when you have two polar molecules, and because the molecule has a positive and a negative side, they're now like little magnets. So think of like our little simulation last time, right? How when something was polar, one side would be very red and one side would be blue. That blue side of one gets attracted to the red side of another. And this right here is the dipole-dipole interaction. It's the magnetic force between the molecules. Okay? Now go back for me really quick in case you didn't do this. On this picture right here, I want you to make sure you circle this. So find this picture on your notes. I want you to circle this dashed line to make sure you know, and then you can draw a line to where it says intermolecular, because I think that's on your notes. But just make sure you recognize this is the IMF that we're referring to throughout all of this, okay?
Mrs. Alviso, can we please have Anders Houghton and Bryson Condi to the C lecture hall?
Yeah.
Okay, they'll be there for the rest of the period.
Oh, that's right. To the Aspire test, and you go. Okay, so it's just a magnet here with our dipole-dipole forces. Yeah, you probably should just take all your stuff.
I think I like another period.
I guess not. But I'll post this video, and then the homework assignment is just the next one in your packet. Sorry. Okay, our second type of force is known as a London dispersion force. I guess you can ask him when you get down there, Anders. Doesn't hurt to ask. I would go down and be like, hey, can maybe let him know a period that you don't care? Like maybe like soccer conditioning or something. It's an easy one to miss, right? Yeah, I would ask him. Doesn't hurt to ask. So, okay, London dispersion is a temporary version of a dipole.
I don't want to leave my phone in that box.
Oh. Okay, it's a temporary version of a dipole. So it's still a positive, negative idea, but it's only temporary. So just by that word temporary, which one do you think is stronger, a dipole force or a London force? A dipole, right? Because this is a temporary dipole. So the way that the London works is, imagine this, okay? So here's our atom. These little black dots are our electrons. Okay, so I want you to pretend for a second that you guys are those little black dots. Okay, and you are the atom. Now, we know that electrons are constantly orbiting and constantly moving inside an atom. So let's say for a second we all stand up and we start running around the room like electrons. Okay? And then I yell freeze. Is it possible that when I yell freeze, there could be more of you on the left side of the room than on the right side? Is that possible?
Yeah.
Yes. And the same thing can happen with electrons. At any given moment in time, the electrons may all be on one side more than the other. So look at our picture here of what happens when the electrons do that. When they shift over, they have now made this side negative and that side positive, like a dipole. It's only temporary though, because those electrons are always moving, so they could just move right back. Okay, but it creates this temporary negative and positive distribution, which is what makes a dipole happen. Okay? Our third type of force is known as hydrogen bonding. Hydrogen bonding is what I would say is an extreme dipole. So if you kind of put them all side by side, we have a dipole-dipole. The London is a temporary dipole. And then the hydrogen bond is the extreme dipole. So they all go back to positive and negative. Now the reason why hydrogen bonding is so extreme is for two reasons. Number one, the hydrogen has a key role here. Okay, so take your pencil here and find this picture on your notes. On this, in a water molecule, who is winning the tug-of-war of the electrons? Good, right? Whichever one is closer to F, has higher electronegativity, it's buffer. So take your pencil and draw an arrow going up from your hydrogens. Now, what happens to our hydrogen when we start pulling its electrons away? Good, it becomes positive. So make little plus signs on the tails of your arrows. that's a dipole. But now the reason why hydrogen bonding is so extreme is, number one, looking at the periodic table, everybody, how many electrons does hydrogen have? Lindsay says 1. It only has 1 electron in the beginning. So if you steal away the only electron an atom has, what do you leave the atom with? Just the nucleus, just the protons. So not only is this positive, but it's very positive. So make your plus sign like exaggerate it here. Okay? It becomes like super positively charged because in a sense you've just left a proton by itself. So when we look at a little water molecule here, in water it's almost like you have oxygen and 2 protons attached to it because you've pulled away all of its electrons. Okay? Now the only way this works, so the second piece, so you have to have hydrogen to get that super positive. But then the thing hydrogen is attached to also has to be a specific element because it has to be strong enough to pull it away enough to make that charge. Okay, so first off, what we just said. First off, we're pulling away its only electrons that it has. And this creates a super concentrated positive charge. So that's what happens to our hydrogen. Now, the only elements that can do this for us are NO or F. So nitrogen, oxygen, and fluorine are the only 3 that are strong enough to cause this hydrogen bond. Okay, so I think of NOF and OF. And they're actually all in a row on the periodic table as well. They spell NOF. Okay? The key thing is the hydrogen must be directly bonded to one of those things. Then the hydrogen bond can form to another. So recognize here, this is not the hydrogen bond. This is the hydrogen bond. It's what happens when one water molecule gets attracted to another. So if I have my 2 waters here, are they going to be attracted like this? Why not? Good. Because in a sense, both of the black pieces are negative. Right? Same thing, they never get attracted like this. Oh, you convinced them. Good job. But how it's going to attract is like that. Right? This right here, that's a hydrogen bond. It's a force between the 2 separate water molecules. Now, the one thing about this IMF that's a little tricky is the fact that we use the word bond in its name. Because it's actually not a real bond. You have a lot of boxes here.
Yeah. Where do you want them?
I don't. Oh, wow. Okay. Let's Okay, so once again, it's not a real bond. My guess of why they call it a hydrogen bond is because it is the strongest of all 3. Now, I would bet that all of you have experienced the strength of hydrogen bonding in your life. If at any time, whether purposefully or not purposefully, you have ever belly flopped into a swimming pool. Because when you belly flop into a swimming pool, the reason why it hurts so much is because of hydrogen bonding. Those little water molecules, where'd my water go? Ah.
Those little devils.
Okay? They're in a sense playing like a game of Red Rover against you. So they're all like hanging on to each other. And so if you hit them like this, I mean, that force is actually incredibly strong. I mean, at certain heights, it's deadly. That's why, like at Lake Powell, you're not supposed to cliff jump from certain heights. It's because you can literally die by hitting the water. I had a friend who got a black eye from water. right? Like water can be extremely hard because of this. Now what happens if you jump into a pool though, like this? Totally fine, right? Because the change of angle allows you to separate the hydrogen bonds from each other. Has anyone ever gone up to Park City before and watched the ski jumpers do tricks into the swimming pool? If you haven't, you should go this summer. It's really cool. I don't know when it happens, or I don't know if it's all the time or not. But what was that? In July. But it's really cool because they pretty much like do ski tricks, but then they land in a swimming pool. But for those that have gone and seen before, what do they do to the swimming pool as they're like jumping and doing tricks? Yes, they have a bunch of jets and they create all these bubbles. The purpose of that is they're disrupting all the hydrogen bonds. Because if you disrupt the hydrogen bond, in case they don't do the trick right, it's not going to hurt. In a sense, they could belly flop into that pool and it wouldn't hurt because you've broken all of the surface tension. It's kind of a similar idea to like foam pits with gymnasts and things like that, of where it allows you to do things without the risk of hurting yourself so much. So, does that make sense? Okay, let's look now and we're going to summarize the 3 types and then I'll show you and then we'll kind of talk more about their applications. Okay, so this table summarizes all 3 side by side. So dipole-dipole is the attractive between positive and negative things, so the permanent dipoles. In order for a molecule to have dipole-dipole forces, it has to be polar. So anything that is polar has dipole-dipole forces. It's our medium strength of the 3, and it can get stronger as the molecules get closer together. So there's our dipole-dipole. London dispersion is our temporary dipole, so the electrons momentarily get uneven. Now, what is it that causes this temporary dipole? What's happening again? Good. The electrons just go to one side, right? It's like all of you ran to the left for a moment. Well, since everything has electrons, everything has dispersion forces. Everything on planet Earth. Okay, it is the weakest of our 3 in strength. Okay, so London is not very strong. But it can get stronger if you have some really big molecules. So if they have a lot of electrons to shift, it can be a pretty strong force. And then finally, our hydrogen bonding. This is our extreme attraction. It's the strongest of them all. But you have a very set requirement of it has to be N to H, O to H, or F to H bonds. If you don't have those, you can't have hydrogen bonding. Once again, the molecules that have it have to be bonded directly to one of those 3. Okay, have to have a direct bond between those 3. It is the greatest strength of all 3. But, once again, recognize it's not a real bond. It is very strong, but it's not as strong as a real chemical bond. I have the strength to break hydrogen bonding by jumping into a pool. But I don't have the strength to break this bond without sending electricity through my swimming pool. It takes a lot of energy to break a real bond. That's why I can't jump into the floor, because those are real bonds, right? But intermolecular forces can be strong, but much easier to separate. Okay? All right, let's look at let's do some practice problems on this. So the first thing like that you need to be able to do, so 11.5 on your ICANs is if I give you a structure, can you tell me what forces it has? So we're going to do the first 3 together, and then I'll have you do the next 3 for some smiley faces. Okay? So look up at your summary box at the top. Look under London dispersion. What type of molecules have London dispersion? All of them. So this is an easy answer because everything, check, 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 has London forces. It's always yes. Every time. Okay? All right, looking at the box again, what does it say for our dipole?
Polar.
So we have to determine if it's polar or not. If it's polar, then it's yes. Non-polar, no. Okay, so looking at this molecule up top here,
Yes.
Yes, it is polar.
yes or no polar?
Yes.
Yes, polar.
It has a ghost. Okay, see, it's kind of around the line. That's why it is polar. Okay? All right, this one, shake your head yes or no. Yes for polar, no for not. Good, not polar, so no dipole forces. Not present. Okay? This one, nod your head yes or no. Yes. What on this makes it polar? One side is different than the other three. It doesn't have a ghost, but one side is an F, the others are H, so yes.
Nuts.
Check. Okay? All right. Hydrogen bonding, number one, it has to have a hydrogen. So the first one doesn't have hydrogen bonding because it doesn't even have hydrogen. Now the second molecule has hydrogen, but it's not NOF. It has to be connected to an N, O, or an F. So nope, no hydrogen bonding. Okay, shake your head yes or no on this last one. What do we think? Good, so it's still no hydrogen bonding. But why? It has an H, it has an F.
But not directly bonded.
Has to be directly bonded. They're not bonded to each other. There's no tug of war going on there. Okay? All right, try the next three for, I guess, technically 9 smiley faces. Because there's 9 boxes. Okay, so try the next 3 with your table buddy. And then we'll check them here in a minute.
So like on this one has
Set your pencil down if you're done thinking, FYI, so I know that you're ready. Okay. Everyone ready? Okay, as I point to them, I want you to shake your head yes or no, okay? You get a smiley face for everyone that you determine correctly. Oh, let's erase what I have. Okay, starting right here, and then we'll go across. So yes or no, London? Very good. Dipole, dipole, yes or no? No dipole, dipole forces. Hydrogen bonding? No. Very good. Questions on the first one? Okay, next one, London forces? Yep, always there. Dipole, dipole? No dipole, dipole. Hydrogen bonding?
yes.
Yes, very good. And last one, London?
Yep.
Yep. Dipole?
Yep.
Yep. And hydrogen?
Yep.
Yep. Very good. So these forces are like additive. They can have all 3, and then it's obviously pretty strong.
Jeez, I'm so good at this.
I'm writing all my Spanish.
Okay, flip to the last page here, everyone. So let's talk about the application of these intermolecular forces and why they matter to us. IMFs, because they are the glue that holds things together, cause substances to behave in certain ways. First one let's talk about is melting and boiling points. So make a side note on this, that the higher the melting point or boiling point means it must have stronger IMFs. if something takes a lot of energy to boil, it's because it's holding on to each other very tightly, right? In order to make water boil, I have to break those hydrogen bonds because when it's a gas, they're by themselves. They're not stuck together anymore. And it's a good thing for us that water doesn't boil super easily. Why would that be bad? One, Moe?
Because we're made out of water.
Number one, we have lots of water inside of us, and we don't want the water inside of us just to boil because it's warm outside, or we have a fever. Right? That would be really bad. Why else would it be important for us? Emily?
It's like the water outside, they got hot and then it's like...
Yeah, things would evaporate so quickly if the forces weren't as strong as they are, and then that would be, once again, not a good thing. So, very good. Okay, some other things that result are this property of cohesion. Okay, does anyone know, I think you talked about a little bit in biology, does anyone know the difference between cohesion and adhesion? Jacob?
Cohesion is sticking from one thing to a different thing. Adhesion is sticking. It's like sticks both ways. So.
Good.
So
Cam, did you want to add to that?
I thought that it was the other way around because like we talked about co is working together, and I thought that it was like co is like water sticking to water, and then
Oh, okay.
adhesion is
That is not a bad assumption because we did talk about how co is like a group of things, but in a sense they are two different things. So cohesion is the ability of water or something to stick to a surface, right? And then adhesion is the ability of it to stick in a sense together, right? Intermolecular forces are an adhesive force, okay? Now with cohesion, this is why water in particular, let's pull up that picture, bubbles up. It forms these little droplets because the water molecules are hanging on to each other. If they weren't hanging on to each other, then they would just spread out, right? So that's how we can get, so these right here, these little arrows, represent like all of the hydrogen bonds grabbing onto each other. So it creates a nice little bubble. Okay? Another cool property of it is something known as capillary action. Okay? Capillary action is the attractive force between a surface of a liquid and the surface of a solid. So this is why if you stick a straw in a cup, and it's a clear straw, if you've never noticed this before, next time, the liquid level in the straw will be higher than the water level that it's in. The reason being is that the water molecules start to climb up the sides and on each other as much as gravity lets them. It gets to a point where they can't climb any higher because pressure's pushing down. But what's cool is the smaller the straw, the higher it can climb. So actually, here's an interesting way to think about trees and how they get their water. They have the teeniest, tiniest of straws inside of their root system. And because it's so small, the water can literally go against gravity, even into the giantest of trees, and reach all the way to the top. That's what capillary action is. If you've ever had your blood drawn, sometimes they'll use a capillary tube, like if they just prick your finger. It's like a really, really thin tube that they just touch to the blood and then just goes up without anyone actually truly sucking it. Because if the tube is small enough, it can just climb itself up the tube. That's what capillary action is. Okay, and then the other one that's super important is the ability to dissolve. We're going to talk about this phrase, and I'll show you my demo here. The phrase is that like dissolves like. When things have similar forces, they have the ability to dissolve one another. If the forces are opposite, then they don't dissolve each other. Okay, this word miscible refers to the ability of things to mix. So right here, in my graduated cylinder, so this is water down at the bottom, and this is oil on the top. I think we're all very aware that water and oil don't mix, right? Now, the reason why they don't mix is not a density thing. Oil's on top because of its density, but I could shake it, they would mix for a moment, but then they would separate back out. The reason why they stay separate is because their forces are opposite. Water is extremely polar because of its hydrogen bonding. The oil is not polar, so it doesn't mix. Now what I'm going to do, I'll turn the light on so you can see a little bit better. I'm going to add a drop of food coloring to this, and I want you to watch what the food coloring does in the different substances or different parts. Okay, I'll bring it around so you can see. So I'll drop. So in the oil portion, can everyone see what the color has done? Let's see, I'll drop another one right here. So what is the color doing in the oil part? Yeah, it's like these cute little spheres, right? It just stays together. So what does that tell you about the properties of the food coloring? Are they the opposite or the same as the oil? They're opposite, right? So the food coloring must be polar. So now watch very carefully as I tap it and I break it into the water layer. Maybe. This worked yesterday. Come on, oil. Do we need more? Make it heavier? Oh.
Yeah, that worked.
Come on, little colored eggs. You just need one to break the surface tension and then it will go. How did this do yesterday? I just tapped it yesterday and it worked. Oh, there it goes. Okay, so as it flows into the water now, what happens to them? They spread out because their forces are similar, so they now mix with each other. So, kind of cool. So this is what we mean by the phrase of like dissolves like. The tall ones? Oh, like for the water, the distilled water? Check the other lab and see if they have any sitting around. If not, there might also be some in the middle table, like in the prep room. Sometimes they're involved. Check there. Okay, so they'll dissolve and mix easily together if they have same forces, otherwise they won't mix. Okay, let's look at that practice problem down at the bottom, and then I'll show you one more demo. Why am I turning this off? I meant to turn this off. Okay, so that problem at the bottom gives us 3 structures. Okay, and then we have some questions we're going to answer about it. So the first question says, put the substances in order of lowest to highest in boiling point. So I'll draw our structures up here so we can talk about them. Okay, looking at these 3 structures, everybody, what did we say? And I have it actually here in orange. So what's the link between boiling point and IMFs? So if I want to put them in order from lowest to highest boiling point, that's pretty much telling you put them in order from weakest to strongest IMFs. So the first thing we need to do is we need to identify what IMFs these each have. Okay, so this molecule right here, does it have London? Mm-hmm. Yes, because they always do. So make a little side note. So this one has London forces. Does it have dipole forces? Nope. Does it have hydrogen bonding? Nope. So London is all it has. Okay, this one would have London because they all do. Does it have dipole forces? Yes, because the F is different from the H's. Does it have hydrogen bonding? No, no hydrogen bonding. Last one here has London. Also has dipole. And also has hydrogen bonding. So to put them in order from lowest to highest boiling point in a sense, they're actually already in order because we're putting them in order from weakest to strong. So you could put, and you just write their formulas. So we put CH4 is less than CH3F, which is less than CH3OH in terms of boiling point. Okay. Second question says, put the above substances in order from weakest to strongest surface tension. So what would be the connection between the surface tension and intermolecular forces? What would make sense? If something has a really strong surface tension, what would that mean about its IMFs? Say it again.
It also has stronger bonds.
It also has stronger bonds. So how would I put these in order from weakest to strongest surface tension? Same order as boiling point, right? Copy paste. Now, number 3, we're trying to identify of the above substances if they would dissolve better in water or in carbon tetrachloride. If you want to write a side note, carbon tetrachloride would be CCl4 because tetra is 4. Okay, so let's go through them one by one. First off, so if we have our 2 dissolving substances, so we're either going to dissolve it in this or in this. First question is, what forces do these molecules have? We know water is polar, right? Carbon tetrachloride is nonpolar. Good. So for our first molecule right here, CH4, which one's going to dissolve it better? Good. The carbon tetrachloride, because it's also nonpolar. And nonpolar will dissolve nonpolar things. So if I had some oil-based colors, because that is a thing, it would have done the opposite of what we just saw. It would color the oil and not the water. Okay? This one, what would be the best choice? Water, because it's polar, and this is polar, so H2O. And then, of course, this one, definitely in water. So when you're figuring out like dissolves like, you're just matching up if they're both polar or if they're both non-polar. Okay, questions on that? So I have a pretty cool substance up here.